Hello dear students. So today we are going to finish the Z transform properties and the system analysis using Z transform. Okay, so we'll be covering the properties also of the Z transform. We'll be covering the properties and the system analysis using Z transform. We'll be also covering the inverse Fourier transform, inverse Z transform. Okay, so these two topics we'll be covering. We'll also cover the inverse Z transform. Okay, how to find out the inverse of the Z transform. Okay. So first of all, let us cover all the properties of Z transform. The first property is a time shifting property. The property says that if Xn is the Z transform, Xn has Z transform Xz, n minus n naught will have Z transform Z to power minus n naught. The effect goes with the same sign. Okay, always remember that the effect goes with the same sign. So in case of time shifting, we have seen that the effect always go with the same sign. Okay, so this property is there. So in this property, there will be no change in the ROC, okay, because there is no change in the format of the signal and neither there is any change in the pole location, okay. Second, delta is shifted delta. We know that delta n has the Z transform equal to 1. So using this property delta n minus 2, the time shifting property will have the Z transform Z to power minus 2. Okay, so these three using the normal time shifting property of the Z transform. Okay, next, time reversal property. Now this property is very important and also it has one attached property to it. Okay, so if Xn has Z transform Xz, X of minus n will have Z transform Xz inverse. Okay, Xz inverse. So remember this property. Obviously, in this property, the ROC will change because the location of pole will change and the format of the signal has also changed. Both the things have changed, okay. This is very important property, that very important conclusion. If Xn is even, then Xn equals to X of minus n, and using this property we can say that Xz is equals to Xz inverse. Okay, so Xz will be equals to Xz inverse. So here we can see that using these things, even signal. So the property here is, if in this case, if signal Xn is even, if Xn is even, if Xz has a pole at P, it will also have a pole at 1 upon P. Okay, at 1 upon P. Okay, so remember this property. This is very important property. Okay, so if the Xz, if Xn is even, Xz has a pole at P, then it will also have a pole at 1 upon P. Same property there is for the 0 also. Same property is for the zeros also. If Xz has a 0 at Z, then 0 at 1 upon Z also exists. Okay, 0 at 1 upon Z also exists. So these two properties, these are very important for pole as well as for 0. Okay. Now, the same goes for the odd also. In case of odd, we have these things. If Xn is odd, if Xn is the odd signal, okay, then xn is equals to minus times of x of minus n, xz equals to minus times of xz inverse. So in this case also the property exists, the same property as existed for even, the same property exists for odd also. Okay, so what are the properties? The properties are, if xz has a pole at P, then pole at 1 upon P also exists. Same goes for 0 also. Same goes for 0 also. If xz has a pole at Z, then, sorry, if xz has a 0 at Z, sorry, then 0 at 1 upon Z also exists. Okay. And with these two properties, there is one extra property for odd, that is 0 exists at plus minus 1 all location also. Zero exists at Z equal to plus minus 1 location also. So these three properties are very important, and if you observe the previous year questions, they have directly asked the questions on these properties. One for even and one for odd. Okay, so remember that whenever signal is even, then if the pole exists at P, the pole at 1 upon P also exists. If the 0 exists at Z, the 0 at 1 upon Z also exists. Okay, so remember these things. Now conjugation in time domain, the property is almost similar to that of the Laplace. Okay, so if xn has the Z transform xz, then x conjugate n will have Z transform x conjugate Z conjugate. Okay, so these two properties, they are very important, and the conclusion is almost similar to that of done in the Laplace. What was the conclusion? The conclusion is, if xn is real, if the signal is real, and it has Z transform xz, Z transform of the signal is xz, then if xz has, or I can say that if I remove this term, then xz has a complex pole or 0, then they exist in conjugate pairs only. Okay, so these three properties you have to remember, one for even, one for odd, and one for the real. So if the signal is real, then the Z transform, that is a xz, will have complex poles or zeros in conjugate pairs only. Okay, will have xz in conjugate pairs only. Okay, will have xz in conjugate pairs. Okay, the complex poles and zeros, not the real ones. Real ones are not important here. Only if the poles or zeros are complex, they exist in conjugate pairs. That's it. Okay, so let us do one question on this. Let us say xn is real and even. Okay, xn is real and even signal with, let us say, pole at 3 plus 4j. Now using the real property, it will say that the pole at conjugate location also exists. 3 plus 4j will have conjugate location 3 minus 4j. Now using the even property, the pole at P will create a pole at 1 upon P also. Will create a pole at 1 upon P also. Okay. So from one pole we can get 4 poles. This due to real, and this creates this due to even, this creates this due to even. Okay. So from one pole we get 4 poles. Okay. So I hope all of you are able to get this property very clearly. Now scaling in time domain. Obviously scaling in time domain leads to loss of information, xn has xz as the z transform. So x of an, let us say if a is greater than 1, then there is a loss of information. For example, x of 2n will have loss of information, and thus the z transform will not have no relationship. Because obviously there is a loss of samples, and if there is loss of samples, thus the z transform of x of n will have no relationship with this xz. Okay. Similarly, if we have x of n by a, okay. Okay, so x of n by a, in this case the samples are not lost, rather we do zero padding. So remember that in this case the z transform will be x of z to power a. So in case of decimation, where there is a sample loss, the z transform will have no relationship. Rather we can find the z transform of this signal if we know this signal, but it will have no relationship with this xz. Okay. But when we do the interpolation or we do zero padding, there is no sample loss, rather we do only zero padding. So in these cases xn by a will have z transform xz to power a. Okay. So this is very important. Great. Next, differentiation in z domain. This property is also very important. If xn has z transform xz, then n of xn means if you multiply by n in time domain, the z transform will be minus z d by dz xz. So remember this property, this is very important. Okay. So let's use this property in an example. We know that a to power n un has z transform 1 upon 1 minus a z inverse. So n a to power n un will have z transform. Using this property, multiplication in time domain by n leads to differentiation in z domain, but with this term. Okay, so minus z, we differentiate this. One upon 1 minus a z inverse, we are going to differentiate this. Okay, so what we'll get after differentiation? If we solve this, we can easily get the result, and the result will be a z inverse upon 1 minus a z inverse whole square. Okay, so this is the z transform of n a to power n un. Okay, n a to power n un using this property. So remember this property, this is very important. Okay, next. So differentiation in z domain. After this we have scaling in z domain. So scaling in z domain means if xn has z transform xz, then xz upon a will lead to a to power n xn multiplication here. This property is also very important. Okay, let's see one example here. So suppose we have 5 to power n un. The z transform here is 1 upon 1 minus 5 z inverse. Okay. Now suppose if we multiply here by 2 to power n. So here we will divide. So if we compare this, if we are multiplying by 2 to power n, we will divide z by 2 in this right side. So this will be the Z transform. Okay. So these kind of properties are very important. Okay. You just have to remember all these properties. Okay. Great. So let's move on. Convolution in time domain. Now this property is also similar to that of the Laplace transform. In Laplace also we have studied that convolution in time domain leads to multiplication in frequency domain or in Laplace domain. So here also if x1n has Z transform x1z, then multiplication or convolution in time domain will lead to multiplication in Z domain or in Z transform. Okay. So this property is used in system analysis also. So this is also a very important property, that if we do convolution in time domain, it will lead to multiplication in Z transform. Okay, or multiplication in Z domain. Okay, great. Now let's see how to find out the inverse Z transform. So this is very simple actually. The cases or the analysis is exactly similar to that done in the Laplace domain. First of all, let us see a very important concept. So suppose we have a Z transform Ci upon 1 minus some constant Pi Z inverse. So this is a term which has a pole at Pi. Okay, we can see that this term has a pole at Pi. This term has a pole at Pi. Okay. Now, if we draw the ROC, the possible ROCs, so we can see that there are two possible ROCs here. One ROC is, so if we draw a circle of radius, circle with radius, magnitude of Pi, okay, magnitude of pole location, we draw a circle equal to magnitude of the pole location. So we have two possible ROCs. One possible ROC is the region inside the circle and one possible ROC is the region outside the circle. Okay, so we have two possible ROCs. One possible ROC is region outside the circle. Okay, now region outside the circle, we can see that the region outside the circle means the signal will be right sided. Okay, do you remember that? If we have the region outside the circle, the ROC will be the right sided signal. Okay, so it will create a signal which is Ci Pi to power n un. Okay, so I hope all of you are able to get this point. Okay, it is exactly similar to the conditions or equations we have studied in the last class. A to power n un has the Z transform 1 upon 1 minus a Z inverse. So this is something like that. So if the ROC is outside the circle, the signal is right sided and we get the signal Ci multiplied by Pi to power n un. Okay, and the second is R less than Pi to Pi magnitude. If we take the ROC inside the circle, then we'll get a left sided signal, and left sided signal from this equation is minus Ci Pi to power n u of minus n minus 1. Okay, so we can see that each pole can give us two possible signals. The same thing is written here also. So Ck, so same thing, exactly same thing is written here. So the signal depends on the ROC. The exactly similar thing we have studied in the Laplace transform also. Okay, so now let us see what is partial fraction, and we know how to find out the partial fraction. Okay, we have done that thing in the Laplace transform. So let's first of all, let me do one example for you, then the things will be very much clear to all of you. So generally xz is written in terms of z inverse. Okay, generally xz is written in terms of z inverse. So something it is written like this, let us say. So we can see that here the variable is z inverse, but in the Laplace we have seen the variable is s. So it doesn't matter, okay, it doesn't matter whatever the variable is, we are not worried about the variable. So for ease of analysis, just replace z inverse by w. Okay, so 1 minus 4w. So it is like this, okay. So now we take the partial fraction of this. So partial fraction will be a upon 1 minus 2w b upon 1 minus 4w. Okay, now we have to find out a and b. We know the method, we exactly know the method. Just don't remember this, just remember the step that we have replaced z inverse by w, and now w is a variable for us. Now we will solve this, we will solve to find out a and b. So a is equals to 1 minus 2w multiplied by this function. Okay, you remember the method, right? And here we will put w equal to this term equal to 0, means this term equals to 0 means w equal to 1 by 2. This and this will cancel out, w equal to 1 by 2 if you put, we'll get a is equal to 1 minus 3 by 2, that is 0.5, minus 0.5, 1 minus 2, that is minus 1. So here we'll get a is equal to 1.5. Okay, exactly similar manner we can find out b also. B is equal to 1 minus 4w multiplied by this function. Then this will cancel out, w equal to 1 by 4 if we put, we will get 1 minus 3 by 4, that is 0.25, 1 minus 1 by 2, that is 0.5. So that is also 1.5. Okay. So I hope all of you are able to get this. Great. Let me check. 1 minus 3 by 4, 3 by 4 is 0.75, so 1 minus 0.75 divided by 1 minus 1 by 2. 0.75 upon 0.5, that is 1.5. Okay, 1.5 is fine. Okay, so I committed a mistake here. It is 0.5 because it is 0.25 upon 0.2 minus 0.2, sorry, 0.25 upon 0.5. So it is 0.5. Okay, here also I committed a mistake. This is also 0.5. So this is what we get. Okay, now we have done the partial fraction of this. Now we can say that xz is equal to 0.5 upon 1 minus 2 z inverse, 0.5 upon 1 minus 4 z inverse. Okay, so this is what we get. Now we have two poles, one at 2, one at 4. We have two poles, one at 2, one at 4. Okay, one at 2 and one at 4. Okay, so this is what we have got. One at 2 and one at 4. So we have two poles. So we created a two circles of 2 radius and 4 radius. Now we can see we have three regions. One is r less than 2. We have three regions. One is r less than 2. Now in this region r less than 2, this one, we can see that this region is inside both the poles. One pole is at 2, one pole is at 4. This region r less than 2 is inside both the poles. So both the poles will be left sided in this case. So this will be 0.5 with the minus sign, 2 to power n u of minus n minus 1. Second one is also minus 0.5, 4 to power n, u of minus n minus 1. Okay. Next, second is the region between 2 and 4, between 2 and 4. Okay. So the region is between 2 and 4. So we can see that this region is outside the pole at 2. Outside the pole at 2. So the pole at 2 will be right sided, and the pole at 4 will be left sided because the region is inside the 4. Okay. So 2 is right sided, 4 is left sided, exactly similar to that of the Laplace. Okay. Now the last is the final ROC is outside the 4 circle, r greater than 4. So in this region r greater than 4, both the poles will be right sided. Okay, because this is the region outside 4. So both are right sided. We'll get 0.5 2 to power n un, 4 to power n un. Okay, this is what we get. So these three are the signals we can get. We have here 3 ROCs. So we have 3 signals which we can get. So generally these type of questions are asked in GATE exam, where we have to find out the ROCs and we have to find out the signals by the inverse Z transform. So whenever the signal is in Z inverse, we convert it into W, we find out the partial fraction, and then we can get the ROCs, and then we can find the inverse easily. So I hope all of you are able to get these points very clearly. Now one more example here. So first of all, we will solve the denominator. 1 minus Z inverse minus 0.5 Z inverse plus 0.5 Z to power minus 2. Okay. So now we will solve this. 1 upon 1 minus Z inverse minus 0.5 Z inverse. Okay. So this is how we can break the denominator. For ease of analysis, we write it in this form. Okay. We write it in this form and then we take the partial fraction. Okay. So now let's find out A and B. A is equal to 1 minus W multiplied by this function and we put W equal to 1. We cancel it, we put W equal to 1 means we get 2. Similarly, we find B. B is equals to 1 minus 0.5 W multiplied by this function . This and this will cancel out. We put W equal to 2 के बराबर. So okay, we put W equal to 2, we get B equal to minus 1. Great. So now we have these terms. We can easily find out the inverse because we know the partial fractions. We can easily find out the inverse. Now we have xz equal to A is 2 . Now here we can see that we have two poles. One pole is at 1, one pole is at 0.5. Okay. One pole is at 1, one pole is at 0.5. So we have regions like this. One pole is at 1, one pole is at 0.5. Okay. So we draw two circles. One circle of radius 1, one circle of radius 0.5. Okay. One circle of radius 1, one circle of radius 0.5. So this is of radius 1.0, one of 0.5. Okay. Now we have three ROCs again. One region is less than 0.5. So here this region is inside both the poles. So we can see that both the poles will give us left sided signal. This will give us -2, u of minus and -1. Second region is 0.5 to 1. Okay, second region is 0.5 to 1. So here we can see that this region is between 0.5 and 1. So outside 0.5, so 0.5 will give us right sided and 1 will give us left sided. So 1 is still left sided. But 0.5 is right sided. And third, r greater than 1, both the poles will be right sided. So this is 2un. Okay, so both are right sided. So this is how we can easily get the signals by inverse Z transform. Okay, great. Now let's move on and see some other properties or some discrete time signal analysis using the Z transform. So this is also very simple, exactly similar to that of the Laplace transform. If you link Z transform with Laplace, you will be very much happy because most of the properties are exactly similar. Okay, so in discrete time LTI system, input is Xn, the system has the impulse response Hn, and the output is Yn. We know that Yn is equal to Xn convolve Hn. So if we convert into Z transform using the property that convolution in time domain is multiplication in frequency Z domain, Xz multiplied by Hz. Okay, so from here we can see that this is the Z transform of output. Okay, this is the Z transform of input. This is the Z transform of Hn. The transform of Hn is Hz, and it is also called the transfer function of the system. The Z transform of Hn, that is transfer function of the system. Okay, transfer function of the system. Okay, so there are two definitions of transfer function. There are two important things of transfer function. First is transfer function is Z transform of Hn. It is Z transform of Hn. Okay, Hn is the impulse response of the system. First thing. Second thing is, it is Hz is equal to Yz upon Xz. Okay, that is, it is equal to Z transform of output divided by Z transform of input. Okay, Z transform of output upon Z transform of input is a transfer function of the system. Great. So you have to remember this. And if you remember or recall, then this transfer function definition is valid only when the initial conditions of the system is 0 or the system is initially at rest. System has 0 initial condition. This is one of the very important condition for the transfer function. Otherwise, transfer function definition or use of transfer function is not valid. Now, Many a times a question is asked where we have to find out the properties of the system using the transfer function. Means a transfer function is given and we have to find out the properties of the system. We know that the transfer function is valid only for the LTI systems. Okay, if the system is LTI, then only the transfer function is valid, otherwise it is invalid. First thing. Second thing is we have to find out the properties. So we know the transfer function is given to us. Transfer function is given to us. We have to find two things. First, we have to find out the causality of the system, that the system is causal or not. We have to find out or comment on the stability of the system, stable or not. So this is what we are going to do in this section. That is, if the transfer function is given, we have to find out the comment on the causality and stability of the system. Okay. So now let us first of all see the condition for causality. So let us see condition for causality or stability together. Now, if we remember chapter 2, that is the LTI system, the condition for stability was Hn is absolutely summable. The impulse response is absolutely summable. This is the condition for stability. We know that condition, we know this condition. Okay. Now, if we remember the property of ROC or the definition of ROC, the ROC is value of R where Hn R to power minus n is absolutely summable. So the value of R where Hn R to power minus n is absolutely summable. This is called the ROC of the Z transform of Hn. So ROC of Hz. Now, if we know that, or if we say that Hn is absolutely summable, if we say that Hn is absolutely summable, if we say that Hn is absolutely summable, then using this condition we can say that Hn is absolutely summable means R equal to 1 is in the ROC, right? If Hn is absolutely summable, it means that Hn multiplied by 1 to power n is absolutely summable. So it means that R equal to 1 is in the ROC. Okay, it means that R equal to 1 is in the ROC. Okay, is in the ROC. So if R equal to 1 is in the ROC of Hz, then Hn is absolutely summable and thus the system is stable. So we can say that if Hz's ROC contains the unit circle, or R equal to 1, contains the unit circle or R equal to 1, then Hn is absolutely summable and system is stable. System is stable. Okay, so this is the condition. This is a very important condition for stability. Great. Now let's move on to this condition for causality. So condition for causality, we know the condition for causality is Hn equals to 0 for n less than 0. Okay. means the signal should be right-sided signal and it should be 0 for n less than 0. Now, which means that the signal should be a right-sided signal. Now, for right-sided signal, the condition is ROC should be R greater than magnitude of the greatest pole. Magnitude of the greatest pole. Okay, so you should remember this very important condition, that for causality, the system should be having the impulse response 0 for n less than 0, or we can say that the impulse response should be a right-sided signal, and thus for that the ROC of Z transform should be, or the ROC of HZ should be of this form, R greater than magnitude of the greatest pole. I hope all of you are able to get this point. Now, here we have one more condition, that degree of Z in the numerator of HZ should be less than or equal to degree of Z in the denominator. Okay, so these two conditions are for causality. Always remember these two conditions. First is ROC should be of this format. Second, the degree. This is very important condition. Most of the books, this condition is not written. Okay, only this condition is written. This condition is very important for causality. Degree of Z in the numerator should be less than the degree of Z in the denominator. Okay. Now, for anti-causal, if you remember, the property is Hn should be 0 for n greater than equal to 0. Means it should be left-sided signal. Hn should be a left-sided signal. Now, for the left-sided signal, the ROC of the format of ROC was R less than magnitude of the smallest pole. R should be less than magnitude of the smallest pole, the first condition. Second condition is degree of Z in the numerator should be greater than equal to degree of Z in the denominator. Okay, so these two conditions are very important. Okay, great. So this is for anti-causal, causal and stable. Now, if we talk about stable and causal, means both together. Stable and causal together means we need that the system should be stable as well as causal. Now, for stability, we need that the ROC must contain the R equal to 1 means the unit circle, and for causality, ROC should be R greater than magnitude of the greatest pole. Magnitude of the greatest pole. Okay, so these two conditions are there. Now we need the two conditions together. So if you just think about it, then we need that the ROC must include the unit circle. The ROC must include the unit circle. So let us say this is the unit circle. This is the unit circle, let us say. So ROC must include the unit circle, and ROC is of this format, R greater than magnitude of the greatest pole. So we can say that the ROC must start from a region or a value which is less than 1. We can say that this magnitude of the greatest pole should be less than 1. Okay, then only these two conditions can exist together. So magnitude of the greatest pole should be less than 1. This is the condition for the stable and causal together. So we can say that if the magnitude of the greatest pole is less than 1, so all the poles should have magnitude less than 1. Great. So for stable and causal together, magnitude of the greatest pole should be less than 1, or we can say that all the poles should have magnitude less than 1. Great. So this is the condition for stable and causal together. So these are the this is how we can like easily do the system analysis. We can find out the Z transform of the output YZ by multiplying HZ with XZ. Okay. We can find out that the system is stable causal or anti-causal or stable causal together by using these conditions. Okay. So this is all for this session. Thank you. Bye bye.